CPU. And so what I'm going to talk about today are a bunch of programs that I wrote really to help the amateur radio community. And I'll just sort of walk through a little bit of the history and how I went about it. I'll step through the 4 different applications, which I did, and then I'll talk about some sort of future projects that I'm working on. So first one's on mag-loop antennas. So I'm not sure if, for those who aren't familiar with mag-loop antennas, they're also known as small transmitting loop antennas. They're relatively small, very high Q, and they provide very low radiation resistance. So to make them an effective transmit antenna, you have to have very low losses. And so typically they're made with copper pipe and stuff like that. So their components of a mag loop would typically be some copper pipe. Most expensive piece will be a vacuum variable capacitor. If you want to transmit with any significant power, you're going to have something like this, and they're usually going to be a few $100s. And then a few inconsequential items like your coax, mounting frame, and potentially a remote tuning motor, because they're very sensitive to their environment when they're built. So tuning them by hand isn't really practical. You really have to do that remotely. And the reason why I decided to make a calculator, so I was when I was in WA, I went to one of those car boot sales, and I picked up 3 vacuum variable capacitors for a deal. It was like for a song. And I thought, well, I'm going to make a mag loop antenna. And you know, I wanted to find a calculator that would make my job easier, that I could sort of optimize according to the capacitors that I had. So some of them had like very limited sort of capacitance ranges and stuff. I'm like, all right, what's this good for? So I had to look around and had to look at the tools. This is probably the best one I came across, 66 Pacific. There's a few different sorts of calculators for amateur radio there. And it kind of makes sense. You know, you put in the circumference of your radiator, of your loop, put the conductor diameter, frequency, and power in it. You hit enter, calculate, and it generates some numbers for you, some predictions. Another one I came across is one from VK3CPU, another web-based calculator. Again, you know, it's sort of web form entry. You put in a few figures, hit calculate, and it'll calculate for you. The thing with this one was that it asks for like enter loop inductance in microhenry. I thought, well, that's not an intuitive thing to enter into calculator, because where would you come up with that? So there's a link to a calculator, so to an inductance calculator on the right there. Here, this was a decent one, K160. So this is 20 years old now. It was developed in 2003, still freely available. I like what the parameters that you put in. You know, they seem to be physical characteristics, like the loop circumference, conductor diameter, operating frequency, and power. So that's sort of pretty good. And then on the right, you can see you can select the units, standard or metric, and then the shape and what it's built from. So this one was really good as well. You could calculate, and it'll generate a bunch of parameters and give you some prediction of your antenna. But however, so far they're all single frequency. You know, I noticed, why can't you produce something with many more frequencies? Why is it just one single frequency prediction? And this is the first one. This is an Excel sheet by Steve Yates, and this was excellent because it did what I sort of wanted. Like, why not do for a particular configuration, what's its performance across a wide range of frequencies? So I thought, oh yeah, this is a pretty cool one. And then I did a bunch of research. So I said, all right, I'm going to learn as much as I can about mag loop antennas. So these are the books. Some of them were from my uni, and a couple others, obviously amateur radio. I did a bit of a deep dive, and I thought, you know, before I develop something, like really get familiar with it. And I find, you know, when I really want to learn something, if you write a little program for it, it forces you to dive in and really learn about that topic. A bunch of papers I read as well. So on solenoid inductance. So you can see there's self-capacitance of solenoids from Medhurst, G.S. Smith. Some of these are quite old. And then the last one there, D.W. Knight, he's an amateur radio, he's still around, did a really excellent paper tying it together, which covered stuff like self-capacitance of coils and stuff like that. So Nagaoka, if you've ever picked up an amateur radio magazine and there's a coil inductance calculator, often you'll see they call about this Nagaoka constant is K, which is the ratio of the diameter of the coil to the length, because there's a correction factor. So the shape of the coil determines the way the magnetic field sort of goes through it, and then you put that into a linear equation, and it gives you a number. This paper I read to learn about proximity effect because I wanted to do multi-turn loops. So if you in a multi-turn loop, when the second coil gets close to the first, you have similar effects to what you get with the skin effect, right? The charge tends to push itself out. So on the bottom left, for two conductors with the currents going the same direction, they sort of oppose, like the current tends to travel on the outside. For opposite, then they tend to travel on the inside, they pull towards each other. So my objective then was, rather than putting stuff on a computer and stuff, I wanted to make it available. Nowadays, everyone uses a mobile phone. So my intent was learn about how to program for a mobile phone target. Use a modern calculator. Modern calculators use today's technologies. Target the mobile phone primarily, although it should work on browsers. If I did it in HTML5 and JavaScript, it can run on pretty much any platform, because any platform that has a browser, it's a great way of distributing software. Then I wanted to use the slider widgets, which is like an intuitive interface that you touch and then slide along. So I didn't want to have this keyboard interface where you're punching in numbers. I wanted to say, well, what if I had a magnetic loop antenna this big, 1 meter wide? Now, what if I made it 1.1 meters wide? You should just be able to scroll and then have the thing respond to user input as you go. So I wanted it to recalculate the complete and predict the complete behavior of the system as you're swiping your finger. So development used Microsoft Visual Studio Code for the code editor, which gives you nice sort of like syntax highlighting. It's really a nice environment for development. And then most browsers, turns out, have really decent built-in debuggers. So as you try to run your web-based program, any issues, you can debug it using the browser. You just enter the debugging mode. And then I stored my code in GitHub repository, which then I later used to actually to host the application. So this is what the input parameters are like. I decided I'm trying to keep it simple. Conductor diameter is the first one. So, if you went to Bunnings and you buy copper pipe, if it's 3/4 of an inch, it's going to be 19 millimeters. So that I thought would be the first parameter that you want to select is your conductor diameter. And then second would be, well, how big a loop do you want? So the second one is selecting your loop diameter. And I thought diameter seemed a bit, I think it sort of feels more intuitive anyway. And then third one, for a multi-loop case, you select N, would tell you how many. Most loops are going to be single loop, but if you wanted to do multiple turns, then you can do it as well. And in that case, when you do multiple turns, the CA is the spacing ratio, is the ratio of the gap between the coils to the diameter of the conductors. And then finally, transmit power. So that would predict the AC currents and the voltages across the capacitor, those sorts of things. So, from entering those parameters, what you can get out then is the expected tuning capacitance for that frequency, the capacitor voltage at that frequency with a certain amount of power, and that's going to be kilovolts. Usually, you're looking at the kilovolts range, even for very small amounts of power. Bandwidth. So magnetic loop antennas are notoriously narrow bandwidth, especially for the lower frequencies. You can be talking like 3 kilohertz, 2 kilohertz. They got very narrow, so your voice will just fit in one channel, and you pretty much have to tune as you go. Antenna efficiency, so that's the radiation resistance over the total resistance, loss resistance plus radiation. Loss resistance and quality factor is interesting, and then loop currents. So these are screenshots, what it looks like. Two of them using your mobile phone. On the left there, you can see it gets cluttered because there's so many dimensions that are being shown on a chart. But you can tap on any of them and you get this sort of little box which says what each value is. And then if you want to declutter, you can actually tap on any of the colored boxes up top, which will silence it, right? So now as you scroll down, you see where the sliders are and a graphical picture of what you're doing. So as you're sweeping, you know, the numbers are changing and it's telling you how big, you get this intuitive feel by the graphic representation updating as you're moving your finger, and then the chart, which predicts all the characteristics. This is how it looks. So the layout changes for when you're using a desktop browser. So, you know, portrait makes sense on a phone. So if you're using it on a phone, yep, great. But then on a browser, you might as well use as much real estate as you can, put it sideways. So the layout changes. You get your scroll bars on the left, and then the visual indicators at the bottom right. Here on the left, you can see now what it looks like if you've put multiple turns. So this is for a 2-turn antenna. So you can see it loops twice on the image. Interestingly, when you put a second loop in a mag loop antenna, a series loop, straight away the self-resonance frequency comes down significantly. So the calculator will reduce the span of frequencies to those that's available. Like, you know, you're not going to be going beyond your self-resonance frequency. And that happens because you get quite a bit of capacitance between the coils. When you push them further, or you get a quite high amount of inductance, sorry. And as you get the coils further away, so if you change the spacing ratio, you'll notice that SRF can then move up. On the right, you can actually calculate also different shapes of antennas. So there's for an octagon. So some people like to build mag loop antennas using plumber's pipes with the elbows, and they're, you know, I don't know if that's is it 15 or 30 degrees or whatever to make a 45. Yeah, you're right. Yeah, 45. Yeah, of course. Yeah, yeah, that's right. That's right. The thing is, and I guess, and this is like people have their own ideas. I think a circle is really great because you don't have the joins. Some people prefer the look of the octagon, but every time you join, you're introducing potential for losses, right? Because you're yeah, and it's going across different metals and stuff. Again, one of the later features I added was support for parallel loops. So series loops, easy enough, and I found one other calculator that did it. So, but then I developed it as well to support parallel loops, which I don't think I've seen another one do. So that's like a new feature. And then on the right are all the different shapes I support now. So there's like a octagon, hexagon, and a square. And square is pretty good because there's only 4 joints. So, you know, you're minimizing the number of brazing or silver soldering your pipe. As you sweep up as well, it shows instructions are all on the same page. So even though when it loads up, it maximizes, you can sweep up. And maybe what I'll do is I'll just demonstrate what it looks like. So if you jumped online and found it, this is what it looks like. So for a 1 meter antenna, as I said, you can tap these and reduce the clutter if you wanted to focus on a few parameters. You know, but oops. But as you go through for 0 to say 30 meg, say on 14 meg, you'll get numbers like 42 picofarads. Bandwidth here is what, 9 kilohertz. 64% efficiency. That efficiency is just based purely on the losses of the conductor. Obviously, efficiency will go down once you consider losses in your capacitor, which will be quite significant. But you can't really model that here. although I've got this RE now that I've introduced to capture other losses. So that would, so once you work out the bandwidth, say with a mini VNC, you can enter that here, and you can see as soon as you start introducing any losses, your performance really degrades significantly. So that would capture losses due to environmentals, like maybe a fence or metal, or ground effect as well. So if I swipe up, you see the instructions are in there, and then change history of what's happened. But also you can click on this equations used, and it sort of brings up a page of how each one of those parameters are calculated. So you can work it out. If you don't trust the calculator, I'm providing the sources in there. Also, I was going to show that this is the way you can debug it in the browser. So you can look at what it would look like for. So at the moment, using this browser, I can simulate an iPad Air and how it would look there. And as I change, as I change the diameter, you can see it's recalculating on the fly. And if you change the conductor diameter, see that. And so for a two loop, let's increase the space between them. So up on there, you can see the inductance of the loop, which is frequency independent. But then as you go onto the chart, that's where you can sort of see the frequency dependent characteristics. Transmit power should only move a few items, which is the capacitor voltage and the loop current, really the only things that change. And if you go to the left and go for parallel, again with the spacing ratio, you can sort of work out characteristics. Okay, let's put something up there. Oh, and this was the paper that really got me into it when I researched Lee Turner. He's now Silent Key just recently. Sadly, he's from South Australia, and he did this magnificent paper. If you wanted to read up on magnetic loops, they're a really wonderful antenna. And his paper I think is like the benchmark paper you'd find on the web. So. Any questions so far? That's essentially the part on the mag loop. Sorry. Oh, did he? Yeah. Okay. Okay, I'm not. Oh, okay, yeah, that's from his paper. Yeah. Okay. The next one was, so after I'd done the initial version anyway, then I got excited and wanted to do a few more different projects. So the next one was to do an RF inductor calculator. So I wanted to do, most inductor formulas are, they calculate relatively simple. But I said, I wanted something that was sort of correct at amateur radio frequencies and had that same sort of idea of using the mobile phone as your interface. So this was the main paper I used, Ninth 2016 paper. Again, fantastic. Source of knowledge. And this is a screenshot, and these are the parameters. So very similar to the magnetic loop antenna, but it's instead of a conductor diameter, it's wire diameter. Then the actual loop coil diameter, it should be. Spacing ratio, of course, number of turns, and then there's a desired frequency. So interestingly, when I first got into this, my experience with wires and stuff was really from JCAR Electronics and buying the 0.5, 0.25, 0.8 millimeter or 1 millimeter, 1.25 millimeter wire. So in my head, I always had that wire was available in metric sizes. And once I dove into it, I realized actually they're not. There's no such thing as metric wires, right? There's these two standards, AWG, which is the American wire gauge, and then there's the standard wire gauge, which is close but not quite the same. So that was interesting. So the first incarnation of my calculator, sorry, was made out of a metric wire standard, which didn't exist. And it wasn't until I got some feedback, somebody saying, "Oh, can you support SWG?" I'm like, "What is that?" You know. So it was really a good learning experience for me, anyway. So then so from the original metric standard, I jumped onto and made a specific one for American wire gauge, and then I did another version for the standard wire gauge, and then I did another version for like coax, so that you can use it now to calculate choking frequency of resonant coax, right? So in your feed, just before you go to your antenna, put a couple of loops. Well, if you use the solenoid style windings, this should get you pretty close. And in fact, it gets quite close to, this is often referenced. I see this on a lot of forums when people want to know what, say the bottom for an air core coax choke frequency response is. A lot of people use this, and I use this to compare to my results, and they're pretty close. Top left, of course, is for ferrite. So if you've wound it through a toroid, and I'll just go and demonstrate that. Yep. Oh, okay. No, I don't. It assumes if you've got the RE, RE assumes free space with 0. So that's the environmental resistance. E is just for like, or external resistance. Generally, the rule of thumb, they say with mag loops, is that you keep it 2 diameters away from the ground. Have you heard differently? Anyone else? No? Yeah, so to get, but no, it doesn't simulate. It's not an electromagnetic modeler. But the idea is if you do measure your antenna characteristics, you can feed that back in because you can measure effective bandwidth, and then you can slide the RE setting until the predictions match what you've measured, and that'll tell you your effective loss resistance of the system. All right. So using this, the first will change the wire gauge thickness. So, you can, I think pretty popular is like, say, 20 AWG, which is 0.8 millimeters. The next one is you pick your diameter. So start off. And for this, I removed the whole metric and imperial thing and just put both available on screen at the same time. So you don't have to switch. So I didn't have to, add that as featured. There's enough real estate to cover both. And the graphic actually stays to scale. So that bottom bit, it maintains the scale of the wire thickness to the shape, so that you can actually visualize it and say, all right, that's how it's going to look when I actually wind it. Increase the spacing ratio, like that. And you can see the inductance in the top left. So the calculations are all in the top left. What it's producing is the inductance in L. C is the stray capacitance, effective stray capacitance. Then you've got your DC resistance. So top left is frequency independent characteristics. And then there's a self-resonant frequency. And then the last one is wire. How long is the bit of wire you're going to need to wind that inductor? And then the top right is what your desired frequency of operation. So if you're designing it for like 7 megahertz, then it's going to calculate the skin depth at 7 meg. The AC resistance, which is in this case, you can see the difference, like 0.007 ohm for DC resistance, but the AC resistance is actually 0.12 ohm, so 120 milliohm. And then it's got your reactance, impedance, complex impedance, and Q. What's interesting is when you get the frequency close to self-resonance. So if I made the diameter really large and increase the number of turns, see the self-resonant frequency come down, say 20 meg. And then when you get the frequency up, approaching self-resonance, you can see how quickly the impedance, the magnitude of the impedance, which I think covered by, yeah, over there, goes up. So you can use this, at least in the coax version. So if I hit coax, to come up with what sort of choking and the cue of that choking for a coax inductor or choke. And again, the instructions are below, so learn how to use it. Just sort of swipe up, and this, yeah, on a how it looks on a mini device, like say your mobile phone is something like this, so you can have it behaving those sorts of behaviors. And that was it for the inductor calculator. And then the next project I worked on was this RF toroid calculator. So I found, a great way to learn, like I said, is actually write a little program. So I thought, a hole in my sort of knowledge was magnetics, the different types of magnetic materials around toroids and that were either ferrites or permanent magnets. So the plan was for me to develop a calculator to calculate the characteristics of either ferrite or powdered iron toroids, to use either as an inductor or suppressor, gain familiarity with different types of cores, and then extend that later onto transformers, which is so I did my research, looked around, and what are the websites? This is probably one of the better websites for a toroid calculator out there. The different types of toroids available on the top left, and then they give you nice dimensions up there, and then you can put in, for a particular number of turns, it would calculate, its inductance and its performance. So I thought this is pretty handy, and actually is quite a popular one online. Another one from 66 Pacific, a little bit more of a simple one. But what I found when I was looking at these calculators, actually they use very simple performance models. So toroids typically have this mu I, which is their initial permeability, and that's what is usually passed around. Like say for magnetic material 43, it's 800. So you get 800 times more magnetization. The field density within the magnetic, it is high, 800 times higher the inductance than it would be with an air core of the same shape. But those are actually measured at quite low frequencies. So usually that's done, those are measured at like 10 kilohertz or 100 kilohertz. That's not in the megahertz range. So manufacturers actually provide these complex mu, they call it. So complex permeability. So there's one, the mu prime, which gives you the real stored magnetic energy, and then mu double prime is like your losses within the core. And none of these calculators actually considered that. And I'm thinking, well, for amateur radio people, we're interested in amateur radio frequencies, megahertz range, but these calculators were treating it almost like they're, we're ignoring the measured data that's provided by the manufacturers. Equations that I used were from Ferrite for the from Ferrite Products Corp for their ferrites. This is a calculator I used to verify my results, which is online. And on the right was actually VK1SV's toroid calculator. So he had a toroid calculator, but all it calculated was the flux density, which I'm not sure what you really use that in real terms, but it was just interesting to see what's sort of out there. So these were my main references. Again, on the left, the data book for ferrite, for ferrites, and then on the right for powdered iron. And this is what the data you'll typically get. So for ferrite material, 43 and 31, very popular amateur radio materials. That chart on the left there shows you the complex permeability versus frequency, all the way on the left for 43 material. Same one for 31 material. And where you cross over, it's sort of saying that actually where those two lines cross is the frequency where your losses are equal to your any energy that you might send through, essentially you're losing half now in the core. So the efficiency is really determined by the characteristics of the core. It's really dominated by your core losses. Again, these are the magnetic design formulas provided by the manufacturer. On the right, say Ferrite provided an Excel sheet of their complex permeability. So I didn't have to look at these and estimate joint dots. Actually, downloaded the CSV for each one of these materials and then loaded into my thing, and it would interpolate. So, you know, they gave very comprehensive measurements, and it's very accurately uses the complex permeability. And then this is what it looks like. So similar interface. First thing you do is select if you want to produce an inductor or a suppressor. And why that's different is that, you know, at certain frequencies, like 43 at lower frequencies, it's a great inductor. But the manufacturer recommends it as it's also used as a suppressor for higher frequencies. So in this case, 43 material acts as a good suppressor at 25 to 300 megahertz. But below that, it's usable as an inductor or a transformer. And then you select the material type. And for ferrites, you can see 75 down to 67. Those are all ferrites. And in the square brackets, I include the initial permeability, which is sort of handy because as the initial permeability goes up, tells you how that you need less windings to get the same inductance. But also it's actually inversely frequency sensitive. So the higher the mu I, usually that's more usable for like lower frequencies. So those higher ones, maybe 75 and 78, are probably really only good for switching, for transformers in the 100 kilohertz range, for power supplies, class D, that sort of stuff. Then as you go with the lower mu's, so material 52, 61, or 67, it has lower permeability, but much better high frequency performance. So lower losses at higher frequencies. Once you've selected your material, then you can select the size. So FT240 is a common size at amateur radio. It's quite big. 240 is essentially saying that the outer diameter is 2.4 inches. So it's old imperial system. And then I've added a few sizes. So sometimes people want to use a stack of 2 FT240s or a stack of 3. So I've added those in as well. Once you've selected your material type, then you select your wire, the size of the wire you're winding, number of windings, and then your excitation voltage and frequency. Actually, is that right? The frequency. Oh yeah, so the frequency down the bottom is different. It shifts the whole frequency because it's so broad. You know, I was thinking, do I do it from like 10 kilohertz to 100 megahertz? Then your resolution isn't very good. So I tended to keep it zoomed around maybe 2 orders of magnitude, and then the frequency changes the span, looking from say 10 kilohertz to megahertz all the way up to meg to 100 meg. So, and then this is for permanent powdered iron, sorry, which interestingly enough, there's not really that many types of powdered iron that's used by amateur radio. Generally, it's going to be type 2, type 6, and type 8. There's only a few of interest. And then maybe a type 0, which doesn't actually have any permeability. It's essentially like what you'd use if you just wanted to use air as your core. And this is what it looks like if you used powdered iron, because powdered iron use colors. So I give a visual indicator of the color. So for material 2, it's red. For material 6, it's yellow. And so I think I might just quickly show what that looks like. So say this is for material 43, FT240. Maybe use, say, 16 AWG wire with the turns, say 10 turns. And then as you sort of move your mouse, you can see what the inductance is at that frequency, what the magnitude of the impedance is, and others. Q, you can see Q is 1 at 7 megahertz for type 43, which is interesting, right? Some people use 43 for higher frequencies, say at 14 meg, but at those frequencies, your losses using 43 material are going to be quite high. You know, so you'd probably want to look at possibly using a different material, say go to 52. Where your Q stays higher for longer at a higher frequency. It doesn't go to 1 until yeah, over 20 megahertz. But if I change it to, say, powdered iron, you'd get the red, yellow for 6. So it gives you, and actually that is a color, that gray, strangely enough. Blue for 17. And 10 for the 0. So most of them are in there, and actually you can use this as the data sheet. And what's special is that actually all the predicted characteristics here are done with the measured complex permeability, which is provided by the manufacturer. One of more recent ones was this loaded dipole calculator as well. So which is used for essentially if you're either a vertical or a dipole. What you can enter in is the frequency when you use it for, and then the percentage of shrinkage, which is the second value. So it starts off, say, at 1. And as you shrink it, then you get your loading coil value increases. And then the next one is about location. And then finally, the wire size. So I will demo that real quick. So say if I wanted to use it for a 7 meg, and full size would be, say, 20 meters, or 10 meters for the half length, right? And as you want to reduce the overall length, so if you're trying to fit a 20-meter antenna, or 7 meg 20-meter antenna into your property, and you've only got a mast for, say, 15 meters bottom to top, or 14. So as you shrink, it's calculating on the fly what the coil should be over there. And then then you can also change the location of the coil, and it's telling you exactly where would it be. Of course, that's just wire thickness, which changes a little bit. And then once you have the inductance value, then you can click on the inductor calculator and whip one up real quick from there. This is probably the simplest one. This actually just uses one big equation that came from one of the ARRL antenna books. And I essentially just put it into something that you can use so that you can sweep the parameters and get calculations in real time. So web links are available. I guess you can just Google the magloop calculator, usually comes up. And lastly, next project. So I've started a couple other projects working on a transformer calculator based on the Toroid calculator. So that's already mostly working, but there's a few things that I'm still ironing out. And the intent is, and maybe I'll just show where that is. That's this one here. So it shows you what the model, what it looks like here. Say for an end-fed antenna, you can change the primary and secondary windings. And you see the ratio there, and then you can actually change the load impedance, you know, what your estimated load impedance is going to be. So as you see your SWR, it'll calculate SWR, magnitude impedance, efficiency, insertion loss, power in, and an S11 parameter, so incidence and reflected. So if you're using one of the mini VNAs, you can sort of cross-check. So this has got a few more because this is a little bit more complicated because you're now modeling a few things. So this is under development. It's not yet ready for use, but that's like a future project. I was going to update the inductor calculator to make it multi-frequency. And lastly, I'm working on actually a electromagnetic method of moments wire antenna modeler. So that's more like EZNEC or MMANA or GAL. So that's under development, and that's a little bit different interface. I'm using a 3D, so you can put in different types of antennas like quad, switch in your ground plane, and it'll generate a pattern for you, which that's what I'm sort of currently working on. But it'll give you a 3D pattern, and you should be able to change the height of your ground, and it should calculate the pattern in real time. So. Yeah, so that's like a work in progress. And that's it. Yeah, I think that's it. Any questions or anything? Oh, Amazon.
Yeah, I've been using Amazon calculators for working out inductors.
Okay,
Inductors I need, and I find that quite good.
Yep.
Yeah,
It's pretty close to the mark.
And some of the charts you had up, or some of the websites up, they've actually used some of those.
Yeah.
Loops, so
Yeah.
I found that quite interesting.
Okay. Cool. Thanks.
Thank you.
Comments coming online. Certainly a lot of work has been done.
Yeah. It's a hobby, so yeah.
It's a hobby, yeah. So everyone's overwhelmed by the whole presentation, and but at least we all know where to go look for. Sorry, I'll get back into frame so you can see what's going on. You want me? I need a mirror so I can look what's going on up there. So thanks again for those who've attended and those online. Hope you've all got something out of that at least, but add to the reference material that's available for us. So Miguel, thank you very much for your presentation. We'd like to give you this.
Oh, awesome. Thank you very much.
Banner of appreciation. You can put it in the office or whatever.
I appreciate
Thank you.
Yeah, cheers.
And for those who are present, there's tea and coffee and bickies in the kitchen. Those at home, you'll have to self-serve. And one last little plug that's got absolutely nothing to do with amateur radio. If you're in the Croydon area tomorrow, Croydon Main Street traders are closing off Main Street, and there will be 120 cars, classics, vintage, veterans, things of interest. So if you're doing nothing else and you would like to wander around, it's going to be a sunny day, I'm promised. Between 10 and 2 tomorrow, but get along, have a look at the cars, and failing that, just keep your fingers crossed for Sunday. It's Father's Day, and maybe there'll be some goodies under the wherever they put them these days, or you just get a voucher and you can go down to Ross and do that sort of thing. So once again, thanks very much for coming out tonight, and enjoy. We'll see you again either on a Thursday morning or the next meeting on the first Friday in October. Thank you.